this lecture is a brief review of a variety of geometry concepts, basically all of which are related to triangles. So the first is just a quick review of the Pythagorean theorem, which tells us that if you have a right triangle, the sum of the squares of the two sides of the right triangle is equal to the squared length of the hypotenuse. I mention this basically because there are a few settings where you're likely to need to calculate the distance between 2 points. So if we suppose that we have this point here and this point here, and we're interested in the length of this line, the key insight that the distance formula gives us is to recognize that in fact the xy grid gives us a right triangle. And so the change in y and the change in x are simply the two sides of a right triangle, and the distance that we're interested in is the hypotenuse of that triangle. So the distance formula, if I rewrite these quantities as they would be for the Pythagorean theorem, can simply be derived by taking the square root of the change in x plus squared plus the change in y squared. As we look at this triangle, just to do an example, here we have the point 4, 3, and here we have the point -1, -2. So in this case, we would take the square of the difference. So I'm going to take 4 minus -1 squared plus 3 minus -2 squared, or the square root of 4 minus -1 gives us 5 squared, plus 3 minus -2 gives us again 5 squared, or the square root of 50. So the length of that line would be the square root of 50. The next topic worth reviewing is the area of a triangle. So basic review, the area is 1/2 base times height. And the key with applying this formula is to recognize that the base is any side of the triangle whose length you know. It does not matter which of the three sides you choose. The height is the vertical distance measured perpendicular to whichever base you're using. So in this case, it would be this vertical distance right here. Now, there are 3 different sides of the triangle, which means there are 3 different base height combinations that we could use. So, for example, on this triangle, if I wanted to use this side as my base, I would need to drop a line perpendicular to the base, and would measure the distance or the height of that line as the height of the triangle. Similarly, if I wanted to use this side of the triangle as the base, I would drop or measure the line perpendicular to that through the vertex. I would measure the length of that, and the length of that line would be the height of the triangle if we were using this side of the triangle as the base. In some cases, this can lead to some slightly quirky behavior. So particularly if we have a triangle that has an obtuse angle in it, like this one, for example, if I wanted to use this side of the triangle as the base, the height would be measured from the vertex opposite that side and perpendicular to the line that the base is on, extended out as far as you need to. Okay, just like with the previous triangle, there are 2 other sides, and so 2 other heights. But it's just worth remembering for obtuse triangles like this, you'll need to drop the height outside of the triangle itself. In practice, the setting where you're likely to end up seeing triangles arise is when you have supply and demand equations, and you're interested in things like the producer or the consumer surplus. So here I have two particular market equations. We typically are going to want to graph these with price on the y-axis and quantity on the x-axis, at least to make it easy for us to see where the producer and the consumer surplus are. We'll end up with, something that looks like this. And up here we have the consumer surplus, and down here we have the producer surplus, two triangles whose areas we might be interested in. So in this case, we'll need to solve the equation to graph it for the price. I'll take QD, I'll move the 5P onto the other side. I'll move the QD onto the other side. And then I'll divide both sides by 5 and get 8 minus 1/5 QD as the demand equation. For the supply equation, I'll do the same thing. I'll move, in this case, I'll just flip the two sides of the equation and then move the 8 to the other side. So I get 11P equals QS plus 8. And then I'll divide both sides by 11 and get P is equal to 1/11 times the quantity supplied plus 8/11. The one additional thing that we might want to do to graph this is going to be, we see here we have the intercepts just fine, but we also are interested in finding a point where they intercept. So I'm going to set the two equations equal to one another just to find the point of intersection. So I have 8 minus 1/5 times the quantity equals 1/11 times the quantity plus 8/11. I'm going to move the negative 1/5 quantity to the right and move the 8/11 to the left. So I get 8 minus 8/11 equals 1/11 plus 1/5 times the quantity. I am now going to simplify all of these fractions. So I do the first subtraction and I get 7 3/11. And on the right hand side, I need to think about getting them under a common denominator. I'll use 55. So I get 5/55 plus 11/55 times the quantity, which is 16/55 times the quantity. And I'm now going to go ahead and finish solving. On the left-hand side, I have 77 plus 3/11. And on the right-hand side, I have 16/55 times quantity. I combine the top on the left-hand side, I get 80. I'm also going to multiply the entire equation by 11, and I get 80 equals 16/5 times the quantity. I'm going to move the 5 to the other side and then divide by 16 and get that the quantity is equal to 80 times 5/16, which is 400/16, which is 25. And then I can plug that into either of the equations. I'll do it here and I get P equals 1/11 times 25 plus 8. And then since 25 plus 8 gives me 33, I get 33/11, or just 3. So we come down and here I have graphed the two equations, and now we're interested in finding the producer and the consumer surplus. To do that, I'm going to need to think about these two triangles. We can see from the equation for the demand that for consumers, which is the area of this triangle that we're interested in, we have the intercept of 8 here, And because the intersection point has a y value of 3, we can conclude from 8 minus 3 that the base of this triangle has a length of 5. Similarly, because we're interested in the height of the triangle, we're going along the x-axis from 0 all the way up to 25, so that that distance right there is simply 25. And we get that the consumer surplus is 1/2 times 5 times 25. Multiply it out. You get 125 over 2. For the producer surplus, same basic idea, except that now we're measuring this distance right here. We're going from a y value of 3 down to the y-intercept here of 8/11. So we're going to have 1/2 times 3 minus 8/11 times 25. Just working that through, I get 25 over 2 times 3 minus 8/11, so it'll be 33 minus 8 over 11, and 33 minus 8 gives me 25 over 11, and I get 25 squared over 22. And I'm done. I've successfully found the producer surplus and the consumer surplus using the areas of the two triangles. At some point you may see areas of more complicated shapes on graphs. In general, when you're in that circumstance, it's simply a question of taking the shape and breaking it into several different triangles whose areas you're able to find. And that will wrap up, hopefully, what you'll need to know about geometry moving forward.